So here's a question that haunted researchers for almost 20 years. You have a neural network. It works. Two layers, cool. It's three layers, also works. It learns, it improves, and everyone's happy. So you think, since two and three layers are working, let's add more layers in the middle. Now, if three is good, 10 should be even better. 100 layers, we should be cooking. Now, as you add the layers and you hit the training button, you will see that the network just dies. No error, no crash. It will just stop learning. The weights will not move, the loss will not budge. Your network is brain dead on arrival. Now you try everything. You'll try changing data. You'll try changing different training methods. You'll try different settings. You'll stay up all night trying to tweak these settings, but nothing will work. And here's the worst part. Nobody can tell you why. Because the math says it should work, right? And theoretically it is working, but something is slightly murdering your gradients before they can do your job. So today I'm going to show you the invisible killer, how it works, why it's so devastating, and clear tricks that you can finally defeat it. So welcome everyone to my channel. If you are into understanding the why behind machine learning and not just a how, make sure you subscribe. We'll go deep on the fundamentals here. So let's get right to it. Today we'll be talking about vanishing and exploding gradients. Okay, before we understand what goes wrong, we should understand what is supposed to go right. So neural networks, what actually do they do when they learn? Basically, neural networks are just a bunch of numbers. We call them weights. Now, these weights are connected together in a structure. Now, each connection that you see here, it has a weight for them. And each weight will make sure that the model learns something specific. And training is just trying to find the proper values for these weights so that the network can give us the correct output, whatever we are trying to understand. Now, here comes the big thing, loss. Now, to find the right weights, we need to measure how wrong we are. That's the loss function. Now, the loss function, you can think of it as a score. Now, high loss means that we're way off, and low loss means that we're doing extremely well. So, our main goal is to try and make sure that this score goes down as much as possible. But here's a tricky part. I might have millions or billions of weights in my network. How do I know which ones to change and which direction do I need to change? Should I increase the weights? Should I decrease the weights? How would I know this? So, this is where the concept of gradients will come in. I'll give you a simple analogy that you can clearly understand so that it's super intuitive. Now, let's say you're blindfolded on top of a hilly landscape. Okay, you want to find the lowest valley, which is right here. Now, you can't see anything, but you can just feel the bottom of the ground with your legs. Now, in order for you to reach this downwards, if you feel that the slope is towards the left side of your left side, you'll move left. If the slope is towards your right side, you'll try to move right. And slowly, as you do this, you'll try to reach the bottom in this way. So you'll try keep going like this and try reaching the bottom over here. Now, this slope, whatever you're feeling, the slope, whichever you're feeling here, that is called the gradient. Now, it tells two things. First thing is the direction in which you want to go and how steep is that direction. These two things, it will tell you that, hey, a steep slope means a big change is needed, and a gentle slope means a smaller change is needed. So now here's where it gets interesting. In a neural network, everything is connected. So the output will depend on the last layer before output. The output will depend on the last layer before output. The last layer will depend on the previous last layer if there exists, and so on until the input. Now, if I want to trace through how a certain value of a weight will influence my output, I have to trace the loss occurred by this weight through the layers ahead of it. So this is called as back propagation. It is usually denoted by something like this. Now, don't stress about the notation. Here's what matters. So, to get a gradient for an early layer, we must multiply together the combinations from all the layers after it. So 10 layers means 10 multiplications. 100 layers means 100 multiplications. And this multiplication operation, this is where the main problem lives. Okay, so let's say we backpropagate. Every time we backpropagate a layer, we multiply by 0.5. Doesn't sound too bad, right? 0.5, it's just a reasonable number. So two layers. Let's take two layers. And if you want to go back, you'll do 0.5 into 0.5. 0.25. This is fine. You go back three layers, which is 0.5 into 0.5 into 0.5. This is 0.125. Now, four layers, that would be 0.0625. Now, 10 layers, that would be roughly 0.001. And 20 layers, we are at 0.000001. So on. So look at that. You can see the gradient just doesn't shrink. It's practically vanished. It's practically zero. By the time the error makes it back to the input layer, it'll be so unbelievably low that these layers almost get zero information about how to improve in the back. If you start multiplying various layers from the front all the way to the back until you get to the input in such a way that, hey, this value is, look at this, it's very, very low, and the weights which exist in the beginning of the neural network will roughly never improve. Now this is called as a vanishing gradient problem. Now the early layers, the ones that are supposed to learn the most fundamental parts of the of fundamental patterns, they're essentially learning nothing. They stay random while the last few layers, whatever we have, will do the actual training. Now, why does this happen? Why is that multiplication factor less than one? So the culprit number one is the activation function. Now, back in the 80s and 90s, everyone used to use an activation function called the sigmoid function. Now, it takes any input and it will convert it into a value which is between 0 and 1, so that it stays nice and bounded, very elegant, and the graph of it will look like a smooth S curve in this way. Now, when we back propagate through the sigmoid, the thing which happens is we'll multiply by its derivative, and the maximum value of that derivative is 0.25. Now, it's never bigger than 0.25. So, every single sigmoid layer guarantees that you're shrinking your data by 75%. Every time you multiply something with 0.25, that means you're shrinking your data by at least 75%. Now, 10 sigmoid layers, you're multiplying this by 0.25 power 10. Now, your gradient is 1 millionth of what it has started. Essentially, that means it is practically gone. Now, the second culprit is a weight initialization. So if you initialize your weights very small, you're making the problem even worse. Small weights mean smaller activation functions, and which means even smaller gradients. So this is still fine for shallow neural networks. But the problem which came when it came to the deep neural networks is that we should add more layers that can learn more powerful things. And every time the researchers try to add a new layer to the neural network, you could see this problem happening. But you might be thinking, okay, what if we just make sure the multiplication is always bigger than 1? That would sort it, right? So let's say you multiply each layer's gradient by 2. For 2 layers, it will be 4. For 3 layers, it will be 8. For 10 layers, it will be over 1,000. For 20 layers, it will be over a million. This number to be precise. And the gradient just doesn't survive. It'll keep exploding as you keep increasing the layer. It'll become astronomically huge. And when you try to update your weights, trying with this passive of a number, everything goes haywire. Your weights swing around wildly. Your loss will shoot up to infinity. Your training will be completely destabilized. So this is called as the exploding gradient problem. And in some ways, this is actually worse than the vanishing gradient problems. At least with vanishing gradients, your network will sit there politely trying to do nothing. But with exploding gradient, your network is actively self-destructing itself. So this problem is especially brutal in RNNs. This problem is especially brutal in RNNs. These are the networks which are designed for sequences and sequences like text, speech, time series, etc. And they process every element one at a time while trying to maintain the memory of what came before. But here's the thing, when you unroll an RNN to train it, you're creating a network with as many layers as, let's say, 500 word sequence. 500 word sequence. That is like 500 layers. Now, these 500 layers, the gradients either shrink to nothing or blow up to infinity. So, that is why for many, many years, RNNs couldn't handle the large sequences. They were only shrunk down to smaller sequences. And if you want to connect information across various paragraphs, that would definitely almost be impossible. So the gradient wouldn't simply survive that whole journey between them. Now, how do we fix this? The entire history of deep learning from 2000 to now is basically the story of trying to solve this problem. So let me try to walk you through the major breakthroughs which we have. Now, first up, a better activation function. Remember how sigmoid will crush the gradients because its derivative is always very tiny? Its maximum value is 0.25. So what if we use something with a nicer derivative? So this right here is a ReLU, rectified linear unit. Now it's almost embarrassingly simple. If the input is negative, the output will be zero. But if the input is positive, which is greater than zero, then it just passes through unchanged. Now, if you look at the derivative for this, if it is lesser than equals to zero, it is still zero. But if it is greater than zero, your derivative is just 1. It's not 0.25. It's not some fraction, just 1. So when you multiply by 1, the gradient will pass through it completely unchanged. Any number of ones you multiply through any number of layers, it will still be 1. So this single swap which we made from sigmoid to ReLU is something which changed everything. It unlocked networks that were way deeper than anything else before. It seems too simple to matter at much, but it is genuinely revolutionary. Now, ReLU has two issues. One thing is called as dying ReLU, and which is where neurons will get stuck at zero. But variants like leaky ReLU has fixed that as well. So the core insight means that you don't strangle your gradients with activation functions. Now, the second solution is smart initialization. The researchers realize that how you set your starting weights of a neural network is also very important. So, if you set these weights very small, the gradients will just vanish. Or if you set these values too high, the gradients will just explode. So, there is a sweet spot. Now, in 2010, Xavier Clorot has proposed a solution. It's proposed an initialization scheme where you'll set the initial weights of a layer in a neural network based on the size of that layer, so that the layer's signals will neither grow or shrink on average as they pass through. And it's not glamorous, it's not a new architecture, it's just setting numbers more carefully at the start, but it made a very massive difference. Now, the third solution is batch normalization. Now, this solution came up in 2015. Whenever you're trying to do backpropagation across multiple layers in a neural network, you would try to set them in a healthier range. If the variants are if the weights of one part of the backprop are very huge and the weights of the other part of the backprop are very less, you would essentially try to compress them into a healthier range together. This will prevent internal signals from drifting to two extreme regions. It can't be either too big or it can't be either too small, and your gradient will be stable. So this is mostly used in every modern architecture we have right now. Now, another solution is skip, or this is also called as resnets. Now, this one's beautiful because in 2015, Microsoft Research, they introduced something called as a ResNet. Uh, this idea is very elegant. Instead of, asking a layer to learn the complete transformation, you'll only ask it to learn the difference. This difference, you'll use it and add it to the original input, whatever you have. It's like building express lanes on highway. So if the traffic gets stuck on a highway, you can divert the people through the expressway instead of going straight through the highway. Now this breakthrough let people train networks with over 100 plus layers, and the original resnet paper showed 152 layers working. Today networks with over 1,000 layers also exist. So skip connections completely shattered the depth barrier. Now earlier today we've talked about something called as RNNs. Now, for these specifically, there were specialized solutions called LSTMs and GRUs. The key feature is that there is a cell state which passes through all the time with minimal modification. So basically acts like a skip connection throughout the cells. And GRUs are much simpler than LSTMs and it has almost similar benefits. And then in 2017, when the transformer architecture became along, and it sidestepped the whole sequential processing problem with the introduction of attention. If you want to go check that out, I've made a video on how attention mechanism works. It will be showing up right above here. Now, but then transformers use layer normalization, skip connections, careful initialization, and everything as well. Now, why does this matter to you? Because this problem shaped everything. The AI winter happened in large part because people couldn't get deep networks on the train. They It concluded that neural networks were fundamentally flawed or fundamentally limited, and they were trying to move on to other techniques. It wasn't that neural networks were a bad idea. Theory was right. The potential was real, but we can't train them. We couldn't just train them properly. Uh, Every solution we talked about today, ReLU, smart initialization, batch normalization, skip connections, LSTMs, each came up with someone asking, why exactly are these gradients misbehaving? What can we do about it? And each answer unlocked new capabilities. And practical lesson for you, if you're training a deep network and it's not learning, this should be one of the first things you should investigate. Check your activation functions, check your initialization, consider adding normalization or residual connections. The tools exist, you just need to know when to reach for them. So that's the story, the vanishing and exploding gradient problem. It is a silent killer that almost ended deep learning before it could begin, and the solutions that brought it back. So quick recap, we've seen that backpropagation will multiply gradients through multiple layers. And if these multiplications constantly shrink things, the gradient will vanish and early layers cannot learn. If they consistently grow things, the gradient will explode and things just start falling apart. Now, the fixes, the first one we saw was ReLU. It keeps derivatives at one, and smart initialization, it will balance the starting point. Batch normalization, it will keep your strengths in a signal strengths in a very healthy range. Skip connections will give you express lane, and LSTMs give RNNs a memory highway. So if you found this video helpful, make sure you go hit that subscribe button. I'll make more videos that go deep onto the fundamentals, the stuff that will actually help you understand what's happening under the hood. So thank you so much for watching. Check out the other videos. I'll see you in the next one.